This is part 2 of our lesson on squares and square roots. In the first part, we learned about perfect squares. In part 2, we will focus on square roots. If you remember our problem from the beginning of part 1, Mayhem and Haas were building a garden. It was a perfect square, and they knew the area of the square. And just like them, this time you will be given the area of the squares. See if you can find the length of their sides. One way that may help you to do this is to estimate how many of our 1 centimeter squares would fit inside these bigger squares. Then simply count along one of the edges of the squares to determine the width. Another way is to use our area formula, A equals W times W, or A equals W squared. Then substitute a value in for the width and see if you get the right answer for the area. Choose one of these two methods and see if you can find the width of these 4 squares. How did you do with your answers? The one thing about finding the width of the square is it's very easy to check to see if we're correct. All we do again is use our area formula. We just multiply the width by itself and see if we come up with the right area. In this first square, if we multiply the width by itself, 2 times 2, we come up with 4, so we know that's correct. The second square, 4 times 4, is 16. Third square, 3 times 3 is 9. And finally, our last square, 6 times 6 is 36. So we know we are correct. Now, the real question becomes, what mathematical operation did you do to actually get these answers? What did you do to 9 to get 3? Or, what did you do to 36 to come up with the answer of 6? What is the opposite of multiplying a number by itself or squaring a number? This is called taking the square root of a number. What would the square root of 25 be? The answer is 5. We know this because 5 times 5 is 25. It is expressed in mathematical terms as follows. The square root of 25 equals 5. That funny symbol in front of 25 is called a radical sign and is used when you are asked to find the square root of a number. Remember, when finding a square root of a number, you are thinking what times itself is equal to the number inside the square root. The number inside the square root is known as the radicand. In Ms. Diller's question for Mayhem, the radicand is 49. Let's see if Mayhem has the right thought processes to come up with the answer. Apparently he does. Now, see if you can find the following square roots in the table below. Remember, when finding square roots, you are thinking what times itself equals the radicand. The radicand is the number inside the square root. Look carefully at these numbers. You should recognize them. Check over your answers. You should see they form a definite pattern. Now, Let's compare the table we just made for square roots with the table we made in part 1 for finding perfect squares. If you take a number and square it, you get a perfect square. If you take that perfect square and square root it, you get your original number. What taking the square does to a number, taking the square root undoes. When this happens, these are called inverse operations. Watch what happens to the number 8 below. First, we'll put it into our square machine, and that will make a perfect square 64. Then, we'll take the 64, put it into our square root machine, and out comes the number 8, the original number we started with. Now, let's go back to our problem involving Mayhem and Haas. What is the minimal amount of fencing they will need to have a perfect square area of 196 meters squared? When solving this problem, Haas and Mayhem will give us some helpful reminders. First, let's take Haas's suggestion and draw and label a diagram. We know the problem involves a square, so we'll draw a square, and the area of that square is 196 square meters. What we want to find is the width, so we'll label that W. Now, we do know an equation or a formula that involves area and width. Area equals width times width, or area equals W squared. Now, let's substitute the 196 meters squared in for area into this formula. What is the opposite of squaring a number? To solve for W, we need to do this. Taking the square root of the number. Now we've got our answer. W is the square root of 196. Let's see if we can figure out what this is. What times itself equals 196? The answer is 14. So now we have our width. But have we answered the question to the problem? How much fencing do we need? That's right, a square has 4 sides. We've just found the length of one of them. So, the amount of fencing we need is going to be 4 times this answer. 4 times 14? Our answer is 56 meters of fencing. Let's summarize everything that we've learned in this lesson. You can create a perfect square by squaring a number. And as Haas says, you can also find the area of a square by squaring one of its sides. You can find the square root of a number by finding a value when multiplied by itself equals the radicand. Remember that radicand is the number inside the radical sign. Also, as Mayhem suggests, you can find the length of the side of a square by taking the square root of its area. Now, Ms. Diller has some fun activities that'll help us continue our learning with squares and square roots. First, a way to memorize the perfect squares and their square roots. Challenge your classmates to see who can recall them the fastest, either by writing them down or reciting them. Another way is to get a whole group of students together and practice counting by perfect squares, each one taking turns. How far can you get? Another activity is to have students create their own functions using square roots, squares, multiplication, division, adding, subtracting, whatever they can think of. Then, a second student can guess what the function is by trying different values and seeing what they get for answers. Haas and Mayhem will demonstrate below. Let's see if Haas can figure out what the function is. He put the number 2 in and got 5 out. Well, that's a good guess, but it's not right. He'll have to try another number. Let's see what happens to the number 5 when he puts it in Mayhem's machine. He got it right. Way to go, Haas.